Cool. So we're going to pick up from where we left off yesterday. Yesterday, we went through the core concepts of integration. We made a lot of pure notes online. All of those are still available on the website. Let's quickly just do a review of what we did yesterday. So the question was, we need to integrate x squared from 0 to 10. Okay, and this we said is a definite integral, and it's definite because the answer is a number. Okay, why is it a number? Because we're looking for the area that's below x squared, so below this graph, between 0, between this point, and between 10, and between this point. So we're looking for the area, essentially, that is below this graph. And just first of all, I want you all to pause and realize, isn't it really cool that we can find the area below the graph by like doing this funny exponent stuff? The first step in this was to integrate. So one is integrate. So we know that this is equal to x cubed over 3, right? The next step is take the difference of the higher point minus the lower point. So what this looks like is up here, when you integrate, you put in the lower point down here and the higher point up here, okay? So then you do higher minus lower. So you do 10 cubed divided by 3 minus 0 cubed divided by 3. And this is equal to 1,000 divided by 3, which is equal to 333.3 the current. Okay, so this is the core concept of integration. Now, this gets tricky when you go into things like this. So what you see is this graph crosses the x-axis. So let's say if we do this in degrees, or we could do this in radians and put 2 pi here, okay? It doesn't matter. The point is, the graph for this, look at that, beautiful. So what we're looking for is, if this is pi, and this is 2 pi, right, in radians, then we're looking for this area in here. Now, let's say I just add these two areas. What will happen? Can anyone guess if I just take this area up here and this area down here and add them up? Exactly, it would add up to 0. Why is that? Because this is a positive area and this is a negative area, right? And they're the same. Both of these are equal to each other. So what we need to do is we need to actually take the first area, this area over here, so let's call this area A, and let's call this area B. We need to do A plus the modulus of B, right? In other words, we know that B is negative, B is equal to negative. We need to do A minus B, and then we get the actual area, okay? So let's do this then. What does this look like? Well, converting this to the next step, this is the part that you guys need to practice because this will come up more and more on the test. So essentially what this means is, what you're doing is you have to figure out you're splitting the curve at this point here, okay? So you do this term plus modulus of this term here, okay? Let's remove this. So that ends up being, what does that end up becoming? The way to do this is step 1, figure out point on x-axis where curve passes through x-axis. Okay. I just want to do a quick poll. Does it make sense why b is negative? It's negative because it's below the x-axis, right? Okay. So you figure out the point. So step 1, in a sine function, this point, we know this point is pi, right? So therefore, here the answer is pi, right? Then 2, you break integral into smaller components, okay? And that's the real math here that needs to happen, which is, if we take this integral here, 0 to 2 pi sine x dx. Here we're going to break it, okay? Break it into smaller portions, which is 0 to pi sine x dx plus modulus, or in this case, what we're going to do is actually plus negative integral from pi to 2 pi sine x dx. Okay, So this is important because what we've done here is, again, if we go back to this graph up here, let's put this back together. Does this work? Nice, it works. Okay. What we're doing is this piece right here is A. This is A, and this is B. Okay. So the area of A spans between 0 and pi, correct? And the area of B spans between pi and 2 pi, right? That is why our limits here are from pi to 2 pi for the second area, okay? So that's essentially the core. Like, if you understand everything that's happened on this page, which is how to do the integration, how to do higher minus lower, and how to break down the integral into its smaller components, essentially you've mastered integration. From here on, it's actually pretty straightforward. All we need to do now is practice, okay? So let's practice this. Let's practice this with a slightly different kind of question, which is, how do you find the area between two curves, okay? So let's do this right now. Again, we're not gonna do the math of integration because we've already done that yesterday. We're gonna do this concept of breaking it down into smaller pieces. So we have a curve x squared, and we have a curve y equals x, okay? So let's draw these two curves out. Let's see what happens. We want to find out the area between them, right? So to find the area between them, what I'm gonna say is that it's equal to, let's do this graph, y equals to x, right? Minus, another graph here. Okay, so I'm saying it's gonna be this area down here minus this area down here. Okay, so you should be able to see how this is now equal to this area on the right side, right? It's very similar to what we did on the day of mensuration. Similar concept. The thing is, how do we find out where's the limit of this area, right? Like how far right are we going in this area? And again, how far right are we going in this area? Well, again, we use the same steps that we did above. So let's go back up. Step one was to find out the point. So instead of finding the point where it crosses the x-axis, we need to find the point where it intersects, which is, which is this point here, right? So we do y equal to x squared and y equals to x. Therefore, y is equal to y squared. And this is true for, or we can do x equal to x squared as well. This is only true for x equals to 0 and x equals to 1, right? So this point is 0, and this point right here is 1. So what we do now is we convert these graphs into its equations. So this is the integral of just x dx, right? Because y equals to x is the term we're integrating. From 0 to 1, from here to here, minus the integral of x squared dx for this curve, right? Again, from 0 to 1, same area. So we want to integrate from between these points. All right, let's see how well I drew this. Am I able to overlay it? Oh, look at that, beauty. I can overlay it, right? So you can understand how the minus works. Good. So this is essentially it. We've broken it down. Now notice, what does not work, this does not work. If I take this minus this, right? That does not work because if you think about it, if from this area down here, you're minusing this larger area, you're just gonna get a negative number, okay? So this approach does not work. The order matters in this case. So keep the order in mind. Let's do this one. I want you to think about this one. So we have two curves here, sine x and cosine x. Let me change this color. Okay, so the white is cosine and the orange is sine x. I want you to take some time and think about how will you break this down? how would you break this down? This one is quite tricky. This is taking into account both things we learned earlier, which is the curve crosses x-axis, right? And two, its area between two curves. Okay, so how would we do this? Okay, all right, so now let's do this together. Let's start from the right, and let's keep going from the right until we hit a problem, okay? So let's do it in purple. So this area, if we start from here, up to here, let's call this 1, okay? This is pretty straightforward, right? This area between two curves, but the curve does not cross the x-axis. So therefore, this is the integral of, what's the higher one? What's above? It's sine x, okay? So sine x minus cosine x dx, okay? So we know that this happens from, if this is pi, then this is half pi. So this is pi over 4, this is pi over 2, right? So pi over 4 to pi over 2, okay? We also know this area in here is pretty straightforward, right? Because it's at the bottom, we do a minus. So we'll do minus, what is it? Minus integral of cosine x minus sine x dx. A question, does it make sense why I did cosine minus sine in this case, whereas here I did sine minus cosine, here I did cosine minus sine? Quick question, does that make sense why? Yeah, this one's tricky. Okay, so I did this because this is a negative. So let's say we take this entire curve, all right, and we turn it around, we flip it upside down, okay? Then this area over here, cosine is above. Whoa, this is upside down. Cosine is above and sine is below, right? In this region, sine is below and cosine is above. That's why we put the cosine first, okay? All right, let's flip the world back to normal. There we go. Okay, so these two purple regions make sense. What about this interesting blue region here? What do we do that? How do we do this? Well, let's split this into region A and region B, okay? So region A, if we take this is just, come out here, under A. Region A is just, if you have a sine curve like this, it's this region, right? Pretty standard. So A will be equal to, are you able to see this properly actually? Let me change color. Okay, so region A will just be the integral of sine x dx. Again, from what points? From pi over 2 to pi, right? So pi over 2 to pi, all right? Now B, what is B? Let's graph cosine x. This region B is from this point to this point. That's this region, right? So it's from where it crosses the x-axis to the minima of the cosine. So this is equal to integral of cosine x dx from pi over 2. No, is it pi over 2? Yes, pi over 2 all the way to pi. Right? Now notice, this is below the x-axis. It's below the x-axis. Therefore, we have to put a negative sign beforehand.
How did you get pi by 4 and pi by 2 as those 2 points at intersection 1?
I sort of got this from the knowledge of sine, which we know the halfway point here is pi, and this point is pi over 2, which is the halfway between 0 and pi, and therefore the halfway point between these two is pi over 4.
Oh, okay. Thank you so much.
Yeah. Hopefully that makes sense. To summarize, what we learned is that this funny integration, though it looks simple, is complex because you have to break it down into 4 parts. Part A, part B, part C, and part D, right? Once you break it down into these 4 parts, it's quite simple from there. So again, what we're going to practice is doing this decomposition, breaking down this into 4 parts, because the rest here is pretty simple, right? This is C, this is D, okay? All right, so let's move on onto the next part. And again, I want you guys to take some time and look at this question, all right? And what I want you to think about is, how can you break this down into its smaller components? How would you break this down into its smaller components and start calculating this area, okay? So just think about this for a minute. Okay, all right, let's go through this. So to find this area, we're just going to ignore these equations for now. Let's call this curve here, oh, let's use a darker color. Let's call this curve here g of x, and we'll call this curve here, let's use f of x, okay? So this is what we'll do. We don't have to work with equations right now. So to figure this out, what you need to notice is that this needs to be broken down into 2 pieces, into piece A and into piece B, okay? And the reason we do this, or let's use a light color for this, A and B, okay? The reason we do this is, let's do the math. So A would be equal to the integral of the higher curve, which is, let's use the same color formatting, g of x minus the lower curve, which is f of x dx, right? Does that make sense? Because here is g of x and here is f of x. We need to find the area in the middle, right? That's A. Okay, what is B equal to? B is equal to the integral of g of x dx only, right? Because from here to here, there's only the area below g of x. Now, the next question is, what are these bounds? Okay, so let's start from the basics. Let's start from here. Well, we've been given the bound here, x is equal to 1. So the lower bound is 1. Now we need to find what's this intersection point here, right? So to find this intersection point, we have to essentially solve for f of x is equal to 0, right? When this function f of x crosses the x-axis, that's when f of x is equal to 0, or when y is equal to 0, right? So we need a point where f of x is equal to 0. So for this purposes, let's say that answer is 1.1, okay? Just for argument's sake, this is not the correct answer, but let's just say it's 1.1. So, sorry, no, not 1.1, let's say 1.5. Okay, so then we go to 1.5. Now, for this area, for B, again, this area starts from this point, from 1.5 to the point they've given us, x equals to 2. Okay? And now we just have to solve for, these 2 integrals using what we learned in last class. What we're doing essentially, we split this into 2 classes. Last class, what we did is I taught you guys integration, okay? To get better at integration, you can only just do practice. And practice problems on integration, you guys can do yourselves. There's a lot of them on the internet. There's some of them on the website I posted, right? Just practicing doing the integration. Today, what we're doing is practicing this piece, the more logical piece and more mathematical piece of breaking down a function or a question into its smaller components, right? And that I want to practice with you because right now on the internet, there's no questions that exist like these, where they break down a complex problem into its smaller solutions, and that's it, right? That's why I noticed today, I'm not going to go through the integration. That's pretty basic practice you can do on your own, but I will go through with you in these more graphical questions and how to break this down and decompose this into its smaller pieces, okay? All right, so let's jump back in. I've got quite a few of these lined up, and let's start breaking these down together. Let's see what happens. Okay, let's do this one. I'll give you guys a minute to think about it. Okay, all right, let's go through it. So again, we'll start from this side. and we'll continue progressing right until we hit a problem. So from here to here is one area. And the reason I stopped at this point is because you have a curve over here, and then you have a curve here, right? But at this point, at the point at here, this new curve begins, right? So we can only integrate one curve at a time. Therefore, this is why we work with the yellow area first. So this area first, this is A, okay? Then we keep going here, and then we've changed curve again. So either the curve changes at the top, or the curve at the top, or the curve changes at the bottom, okay? Then you stop. So the curve changes here at the bottom. So we draw a line up from here. This is area B, okay? Now we have a new curve over here, new curve. And notice the curve at the top stays the same, still the same, still the same, still the same, all the way to this point. So this is C, okay? So let's just write these out really quickly. A is equal to the integral from the top curve. So top curve is this, 2x squared, minus the bottom curve, which is 2 dx. B is equal to, let's use a darker color here. B is equal to, from this point, so the top curve again, from 8 minus the integration, the bottom curve, 2 dx, okay? And C is equal to the top curve, which is 8 minus the bottom curve, which is x squared dx, all right? Now we need to go through and find these points here, right? This is pretty straightforward now. Yeah, I'm not gonna go through this, finding these points. This is just doing simultaneous equations, okay? But you find points from sim equation, okay? What is important to know, however, is let's just erase all of this for a second. What's important to know is I'm just gonna put in the values. So we're gonna call this, let's call this small a, let's call this small b, small c, and small d, okay? So on this side, this curve goes from A to B, right? This area. This area goes from B to C. So from B to C. And this area here goes from C to D. So from C to D, okay? We have a great question, which is, can we just flip this around? How would we flip this? Let's see, does this work? Rotate, can I rotate this? Yeah. There we go. So can you just flip this around? And what happens? So if I flip this around, I start at this point, my curve is same, my top curve is same. I keep going, yep, my bottom curve is same, my top curve is same. Easy, right? So this is just, this entire area is only one integral. Yes, you can do that, and that is okay if you want to do that. I am not going over it because it adds this additional complexity of changing the equations. You have to go from y is equal to x squared to x is equal to square root y. And then you have to do the integral with respect to dy. You can do that. It's a similar concept, but in this case, I'm not going to go through it because I don't think it's too, directly applicable to you guys. Most of your questions are actually been coming around doing it doing it this way up with y being above, okay? Okay, let's do this one. Let's do this now. I think you should be able to see this pretty quickly, that we have two areas here. This bottom area here is the same as this curve here. So we stop, this is A, and then bottom area here, B. Now this is a really good question. I like this one quite a bit because let's make this equal to f of x, and let's make this equal to g of x, okay? So this portion right here, whoa, what just happened? Wow, okay, cool. Let's highlight these curves accordingly so we can see what we mean. F of x is this curve here, right? And g of x is this curve here, okay? So the answer for A is equal to the integral, but what's the higher curve? It's g of x. G of x minus the lower curve is f of x, dx, right? And then B is equal to the higher curve, which is, in this case, f of x, minus the lower curve, which is g of x, dx, right? And how do you get these points? Well, this point is pretty straightforward. This is 0. Now, where does 0 go? Well, 0 goes at the end point of the B area, right? The end point of B area. So that would be this point here. No. Yes, this point here. Would it? Hold on, let me think about this. We're gonna do.
Shouldn't it be above?
Yeah, I think it should be above. Yeah. Yeah, because it's from the lower to the higher. So from this point to the higher. Yeah, good. So because this is the highest point, that's why 0 is above. Good. These 2 points is just simultaneous equations. You equate f of x and g of x, and that's how you get these 2 points. Okay? So that's pretty straightforward. Good. Okay. All right. Let's keep going. All right. We've done something like this. This should be pretty straightforward. So 2 areas. This area here, A, and this area here, B. Okay. So let's do this. A is equal to the integral of the higher, which is 3 sine x plus 1, minus the lower. And notice how the lower, essentially, this is y is equal to 0, right? So you could do minus 0 dx. You could do that, but you don't need to do that because it's minus 0, right? There's no point of doing minus 0. So essentially, this becomes just that integration. Let's put in the points. Let's say this point is, point lowercase a, and this is lowercase b. Or actually, no, they've given us letters. Let's use the letters that they've given us as 0, a, and b, right? So this is from 0 to a. And then let's do the next area. B is equal to the integration from a to b, right? Of this curve 3 sine x plus 1 dx. Now, answer equals a plus b. Quick poll, is this true or false? So the question is this correct? Answer equals a plus b. Is this correct? Where a is this area and b is this area. Quick poll. Yes or no? Is the answer equal to a plus b? Yeah, it's the answer is no. The answer is no because remember, b is negative. This is a negative term, right? Because it's below the graph, this is negative. And this here is positive. So if you add a and b, essentially you're removing a b area from a and you're only looking at this area. So you can't do that. We need to change this term here to a negative. So it has to be a minus b. Or you put a negative here and then this becomes a plus b. Okay, it's very crucial you understand that. All right, let's keep going. All right, I'm gonna change up my naming system. I think the naming system might be confusing. So, okay, if we go from here to, oh, the bottom curve changes. So we stop, it changes. Okay, so this is R1, region 1. R1 means region 1. Keep going, bottom curve, same, above curve, same. We stop, above curve, same, stop, R2, okay? So R1 is equal to integration of above curve, which is this term, 3x squared plus 2x cubed, minus the lower term, which is negative x, minus x dx, right? And R2 is equal to integration of higher curve, which is minus x, minus the lower curve, which is this term here, 3x squared plus 2x cubed dx. I'm not sure if you can see this. There we go. This is much better. Okay. I picked a different notation here because if this is point A, let's say this is point, let's use this color. Whoa. This is point B, and this is O, right? So we go from A to B in this region, and then from B to O, from B to O for this integration. All right, hopefully you're all with me and you're getting this. Quick poll, are these questions becoming easier and easier as we go along? The more we practice, is this becoming easier and easier? Yes or no? Okay, good. Hopefully it should be becoming easier. If not, then just keep doing more practice like this. Okay, let's do this one now. All right, so how many regions are there? Can you put into chat how many regions are in this question? Good, yeah, 2 regions. Good. So if we go here, we have to stop because the higher curve has changed. The curve above in the maximum has changed. We can't keep going. It's changed to a new curve. So we stop. So this is R1. And this is R2. Okay. Let's do this again. So R1 is equal to integral higher curve, which is this curve, e2x plus 1, minus lower curve, which is this curve, minus x plus 2 dx. Okay. And R2 equals to integral of lower curve, higher curve, which is now y equals 4, minus lower curve, which is this term here, minus x plus 2. And notice I'm putting this in bracket. Don't make an error with the minuses, yeah? And again, let's come and figure out the point. So this is O. This here is A. And this term here is B. So this term goes from O to A, right? From O to A. And R2 goes from A to B. So from A to B. Oh, we're done. Oh no, I'm out of questions. Do you guys want more questions? All right, we'll do 2 questions. Let me just make up questions then. All right, I'm out of questions I prepared for you. So let me just make them up. Okay, and I'm gonna make them really complicated. Okay, so let's see. We need to find this region here. Yeah, this is very much possible. The 2 areas don't have to be touching. Like you don't need to have, like the areas don't have to be touching each other. You can have two obscure areas next to one another. Okay, so let's give these. Let's call this point A, point B, point C, point D. Finding A, B, and C, D will be a little tricky because you have to basically do tricks with the sine curve, but we're not going into that. The point is, let's say this is sine x, and let's say this is equal to y equals 0.5, okay? So we have R1 and R2. So R1 is equal to integral from A to B, correct? Of the higher curve, so of sine x minus the lower curve, 0.5 dx. And R2 is equal to integral from C to D of the higher curve, again, sine x minus the lower curve, 0.5 dx, okay? Yeah. Notice how B and C, like notice how initially, usually, if we go up here, the higher and the lower of two different integrals were the same, right? Because they were touching at this point. Or if we go here, again, they were touching at this point. Oh, we didn't do it here. Here they were touching at this point. So the B and the B were the same, and the C and the C were the same, right? So, but in this case, they're not touching. These two areas are not touching. So the area B and C are not the same, okay? That should intuitively make sense. Someone is putting a really good point, which is take 1 and multiply by 2. This is really, really important as you keep going, because you should notice that R1 is equal to R2, okay? And actually, this is not the first time we've encountered this. If we go up here in this question, okay, we have to notice that C and D are the same. C equals to D and A equals to B. Okay, you guys should notice that. So really, you only need to do this integral here and this integral here, add them together and multiply by 2. Okay, if you notice this, perfect. If you don't notice this, that's fine. It will take you longer, but as you're going through these, especially with repetitive functions like sines are repetitive, right? Or with reflective functions like x squared, they reflect across this axis, right? You should notice that some areas are the same. It's only with repetitive or reflective functions this works. So if you have a graph like let's say we do the tan graph. Let me do this one question that's coming in: how to do an area between below an asymptote. Okay, so I think it doesn't really matter actually if you have an asymptote. Let me show you why. In the tan graph, I think it's like what? It's like this, right? Essentially, and this becomes the asymptote. So if you had to find this area down here, you can't really find it because the integral is from 0 to pi by 2, tan x dx. Then if you do the integral, what does tan become? If we go to the rules, what does tan become? The integral of tan, oh, we don't have integral of tan. Essentially, the question is if you convert this to whatever the answer becomes, like f of x, let's say, is equal to f of x, you go from f of x from 0 to pi over 2, right? So it's f of pi over 2 minus f of 0. I think at the asymptote, I think this may equal to infinity. So I think that won't work if this equals to infinity. Now, on the other hand, if you add another line to this, let's remove all of this. And let's say you add another line like this. Okay, then there's just two regions. There's region A and region B, right? And you don't need to worry about the asymptote because the asymptote doesn't matter, right? Region B is coming. It doesn't matter. It doesn't deal with the asymptote, so that doesn't really matter. Ooh, yeah, this one's tricky. How many areas are there? Okay, all right. So we've got quite a few guesses, and if you're making mistakes, that's fine. We have 2, 4, and 5. Okay, so let's start going through this. Let me remove this big green area. So let's follow the approach we do usually, which is, let's use this color. You start at this point, you move here, and notice that once you reach this point, the bottom curve changes. So you stop, the bottom curve changes. Why? Because we start going into negative territory. We don't want to go there. So this is A. Okay, then we stick with this curve here. We stick with this curve and the bottom curve. And oh, we have to stop here again. Why do we stop here? Because the bottom curve has changed to a new curve, right? So this is B. Then we keep going here and here. This is C. Okay. Then we start again on this side for the above area. So we go here and here. Okay, so far so good. Keep going, keep going, keep going, keep going. Oh, now we stop here. Curve has changed. So this is D. And the last area is this baby here, E. Okay, so 1, 2, 3, 4, 5. 5 is the correct answer. All right, so we'll stop here for now. Today actually is supposed to be the last day of these classes. Do you want this class to keep going? Do you want more of these classes? Okay, all right, this makes me quite happy. All of you, 100% of you want more of these classes. Has this class helped you enjoy math more? Okay, awesome. Somebody's put a lot of a yes with a lot of S's in chat. That makes me quite happy. Have these classes been more fun and engaging than your other tutoring and school classes? 100% of you. That makes me happy. So let me send you out with a little bit more of Lord of the Rings.